We'll be looking at 4 common mistakes students make in complex number questions in Cambridge 9709 paper 3. These are small errors, but they often cost easy marks in exams. Many simplification errors come from forgetting that I squared is equal to negative 1. So for example, if you have 3I squared, you need to replace that with negative 3. And similarly, we need to also remember that all other powers of I have to be simplified. So for example, I cubed would be I squared into I, which is negative 1 into I, which is negative I. Forgetting this rule leads to incorrect answers later in the question. The second mistake that students make is not separating real and imaginary parts. Now, many of our answers depend on us being able to identify the real and imaginary parts of a complex number. So if you have something that looks like this, let me give you an example. Suppose your complex number is this, 3a squared plus 2ai plus 3b minus 5ai squared, the whole thing over 3a minus 2b. Right, this is a complex number, but right now it's kind of hard to figure out which is the real part and which is the imaginary part. So I'm going to simplify it. So the first thing I want to do is replace all the I squareds with negative 1. So 3a squared plus 2ai plus 3b minus 5a into negative 1, the whole thing divided by 3a minus 2b. And that further simplifies to 3a squared plus 2ai plus 3b plus 5a, the whole divided by 3a minus 2b. Next, we want to do the separation. So how do we do that? Club all the terms with I together and all the terms without I together. So 3a squared plus 3b plus 5a are all real parts of the numerator, and then plus 2ai is the imaginary part, and then I'm going to divide that by 3a minus 2b, and now we're going to split the numerator into real and imaginary parts, remembering that 3a minus 2b, the denominator, goes under both the real portion and the imaginary portion. So it's going to be 3a squared plus 3b plus 5a, the whole divided by 3a minus 2b, that's the real part, plus 2a I over 3a minus 2b. So now we have separated that complex looking complex number into its real and imaginary parts. The third mistake is the argument not being in the correct range. Now, according to your syllabus, the principal range for the argument of complex numbers is minus pi less than the argument of z less than equal to pi. That means your argument has to always lie between minus pi and pi inclusive. Now when you're doing things like, suppose you have two complex numbers, u and v, if they're asking you to divide them, so u by v or u into v, in that case, you might end up with an argument that does not lie in this range of minus pi to pi. So then what do? You have to adjust it. How do you adjust it? Adjust by adding or subtracting 2 pi to bring it within this range. So I'll give you an example. Let's say you found arg z is 5 pi by 2. Now 5 pi by 2 is greater than pi, right? So it doesn't lie in this range here. So we have to adjust it by subtracting. So take your 5 pi by 2. In this case, we're going to subtract 2 pi from it. So we'll end up with pi by 2, which is now in the range. Right? So instead of writing 5 pi by 2 as the argument, you'll write pi by 2. Similarly, let's say you have the arg value of z as negative 3 pi by 2. Now, negative 3 pi by 2 also doesn't lie in the range minus 2 pi. And in this case, in order to bring it into the range, we're going to add 2 pi. So what do we get in this case? We get pi by 2. Just remember that whenever you calculate an argument, the first thing you do is check whether it is within the range minus pi to pi, and if not, add or subtract 2 pi until it comes within the range. So you might have to add or subtract it multiple times to bring it in the range. Fourth mistake has to do with forgetting that complex roots come in pairs. So if you are solving a polynomial that involves complex numbers, usually they will give you the first root. So say they tell you that the first root is 2 plus 3i. We immediately then know that the conjugate of 2 plus 3i, which is 2 minus 3i, is also a root. So complex roots always come in pairs. I'm going to also show you what they look like on an Argand diagram. So let's say I'm going to mark 2 plus 3i and 2 minus 3i. So if this is 2 plus 3i right here, its conjugate pair, or the pair of the complex root, would be here, 2 minus 3i, and vice versa. And similarly, if you have a complex root here, let's say this is negative 1 plus I, this one's conjugate pair would be here, and vice versa. So this would be negative 1 minus I, and if they gave you the root negative 1 minus I, then your complex root would be in the second quadrant. Just like this. So pairs of roots are always paired like this in the first and the fourth quadrants and the second and the third quadrant. This is also useful for you to know, especially when you're rooting complex numbers in exponential form, let's say. So for example, suppose they give you a complex number, u is equal to 3 e to the power of pi by 6 I, and ask you to find the root of this complex number. So remember, they come in pairs. So if I root u, I can say 3 e to the power of pi by 6i to the power of half on the right side. And then I apply that root to both the terms. So 3 becomes 3 to the power of half, which is root 3. And e pi by 6i into half, right? So this is root 3 e to the power of pi by 12i. Right, so this is the first root. The second root you can tell because pi by 12 lies in the first quadrant. Therefore, its conjugate should lie in the fourth quadrant here. Okay, our principal values for not argand, for arguments of complex numbers go from pi to minus pi. This is 0, this is pi by 2, and this is negative pi by 2. So you go anti-clockwise from minus pi to minus pi by 2, 0, pi by 2, and pi, right? So if I found my first root, pi by, and its argument is pi by 12, it's in the first quadrant. Therefore, the second root must be in the fourth quadrant. So that would be, it would have the same modulus, so root 3. And if I had to find, so let's say this is pi by 12, just for the sake of demonstrating it. If this is pi by 12, this would be another pi by 12 here, right? So you can figure out the argument of the second root by drawing out a quick argand diagram. So this is negative pi by 12 in the fourth quadrant. Alright, so don't forget that if one complex root is given to you, there is a second complex root which is a conjugate, and if the original root, original complex number is given to you in exponential form, this is how you figure out the two roots of the complex number. So the 4 mistakes to watch out for are forgetting I squared is equal to -1, not separating real and imaginary parts correctly, writing the argument outside the correct range, and forgetting that complex numbers occur in conjugate pairs. So if you avoid these mistakes, you can secure easy marks in your complex number questions in 9709 paper 3. We have also solved a whole bunch of past paper questions of different types in a different video. I will leave the link in the comments.